How do you prevent somebody from installing tab A into slot B and destroying a $1 million sensor? And how can a scatter plot save lives? These are the topics we'll be discussing today on Engineering Aerospace. Welcome to Engineering Aerospace with me, Eric Kane. Here we'll be talking about topics that affect the lives and careers of aerospace engineers, develop the skills that'll help accelerate your career, and just have fun talking about our favorite industry. And today I wanted to talk about two major topics. One is about the keying and selection of electrical connectors, and the other will be lessons learned from the Challenger disaster and how that can improve your communication skills. So let's get into our first topic for today. So if you're involved with designing electrical installations, avionics boxes, cabling, etc., one of the things you'll have to consider is the keying of your connectors. And so what I have here is an example of a box that has two connectors of the same size. These connectors might have different functions, and I want to be able to prevent someone from putting the connector that goes into J3 here onto the J2 connection. And so what I would do if I were trying to prevent that is to key the connector. Now we could label those connectors, but someone could screw that up, obviously. So if they're not paying attention, they don't read the connection or the label on the connector, then they might actually accidentally put that connector in the wrong port. So a story I had heard, this is secondhand from somebody else, but there was a Special Forces C-130 aircraft that went under some maintenance a while back. And this aircraft had a large optical sensor turret. So these are the kinds of things you see night vision cameras or infrared cameras and optical images that they can use from a long distance. So it's a big, expensive piece of equipment. And they had this installed up on the forward end of the aircraft. Now, because of the size of that, they could not have that deployed while they were landing and taking off. The sensor got stowed up into the aircraft when it was taking off, when it was landing, so that they could allow the landing gear to deploy and not hit the sensor on the ground. So in this case, some maintenance techs worked on some equipment up there and apparently swapped the connectors from where they should have been. So perhaps one of the connectors was supposed to go to the sensor turret, another one was going to the mechanism, the motor that drove the turret up and down. Well, since they got these connectors swapped, crew went to go turn the power on to activate the sensor and check it out. But instead of activating the sensor, it turned on the motor system, and that drove the whole sensor turret down through a landing gear door and basically broke that landing gear door. And so you turned your multi-million-dollar sensor into a battering ram because someone put the connectors in the wrong spot. So how do you prevent that? Well, the simplest answer is to make it impossible for someone to put the connector in the wrong location. So this is a technique we call keying. So I'm going to go to the tablet here, and we're going to show you what the keying might look like. So if this is the circular connector that we're so often seeing in the aerospace industry, and you can do this on other types of connectors as well, they often provide some sort of tab features, something that sticks out on the connector or on the receptacle side. Usually it's a depression. So you have these interfacing features. Basically, your connectors are not going to be interchangeable. So even though they may be the same size, unless your connector has the right key feature, it will not interface. So in this case, it's got two keying features on it, and your mating connector has to have the same matchup. So if I had another connector off to the side, which perhaps had the same feature on one side but not on the other, well, that would not interface with this connector, and so that would prevent someone from physically installing it in the wrong spot. And so if you look at the specifications for a lot of connectors, they will provide a key feature, and a lot of times this is a part designation, it'll have the description as to which keys you can use, and often they're just listed as like A, B, C, etc. So you can use key A with the two connectors. So the one side's the plug and one side's the receptacle, and they'll have the same key to match up. And then when you go to the second connector, you might use key B, and the third connector you might use key C. And so that way, even if all three of these connectors are right next to each other, they look almost identical, they're the same size, you can't accidentally put one in the wrong spot because they are keyed differently. And so that's the most common method we use to prevent accidental connections in a setup like that. Because if you just use labels, if you use other ways to try and tell somebody what connector goes where, if it's possible for them to screw it up, they probably will. And so anything you can do in the design of your system to prevent the human from creating an error down the future, the better. So even somebody who's not paying attention will realize that connector doesn't fit in the right spot, and that that's not the place it goes. So I hope that helps, and keep that in mind the next time you're working on selecting connectors. Now, another important timely topic I want to discuss is that I am recording this on the 29th of January 2026, and that means yesterday marked the 40th anniversary of the Challenger disaster. And as tragic as those events were, I think events like that also provide a great opportunity for engineers to learn lessons and find ways that they can leverage the experiences of the past to help improve the future. And so that also helps the legacy of those that suffered and died in that incident to make it not in vain, right? Which is to leverage the lessons that should be learned so that someone else doesn't have to experience the same experience. So I wanted to spend a few minutes discussing something that I think is relevant specifically to engineering and in general that can be learned from the shuttle disaster. And in the future, I may go into more in depth about what exactly went on during that incident. But one of the important lessons I think that could be taken out of that Challenger disaster is a lesson on how to present data as an engineer. Obviously, as engineers, we're very technical. We work a lot with numbers. We do a lot of development and presentations that we provide to management, to other engineers, to help communicate our thoughts, to document what we've done, and to help us make decisions. And obviously, the decision to launch the Challenger in hindsight was a very poor one, but there were definitely signs but prior to the launch that decision could have been made differently, and some of the events that took place kind of outlined how poor information communication, poor testing, understanding of the problems exacerbated into a complete failure of the system. And if you haven't already, I think it would be worthwhile to take a look at the accident report for the Challenger disaster. You can just search for Challenger accident report, and NASA has a link for a PDF copy of the report that was provided back in 1986. And you can read through that. Some of the quality, of course, is not up to modern standards, but it was written out and recorded now in electronic format. And there's plenty of videos out there as well on the details of what happened, and you can read about it in a variety of books and other contexts. But what I wanted to talk about today is the discussion around how data related to the O-ring problem for the solid rocket boosters on the shuttle was presented, and how it could have been presented and understood more clearly. This is an example that's used often in engineering, and so I'm not necessarily repeating anything new or innovative. In fact, I was taught this back when I went to school, but not everybody has been taught this, and I think it's worthwhile, even if you have, to get a refresher that how important it can be for us to clearly present our thoughts, clearly present the data, and understand the variables that are involved. So if you're not familiar with the solid rocket booster design, the solid rocket boosters were built out of major sections. So Thiokol at the time was the company building those boosters, and the same basic design is still being used today in the SLS launch vehicle, with modifications, of course. But the idea behind the general concept is that you have these large solid fueled propellant systems that are assembled in pieces. Now the segments, it's broken into, I believe, 4 segments on the shuttle. I think the SLS actually uses 5 today, but the 4 segment boosters, they're called such because they are shipped to the launch site in those segments and then assembled in the vehicle assembly building. So those points where the components come together are called field joints. And so when you're assembling the rocket in those field joints, they have to be sealed such that obviously you don't want the hot rocket exhaust leaking out between each of those joints. And so there was a process developed, and there were a variety of structural members that were created to help contain the rocket exhaust, as well as putties and a variety of materials. But there was recognized that there was a problem with the design of those solid rocket boosters, in that they started having issues where under certain flights they used these rubber O-rings that help to seal the pressure inside the motor at those field joints, and sometimes hot rocket exhaust would leak between them, or they would get damaged in some way. And so there was starting to be a record of these failures being recorded after each mission, because of course the solid rocket boosters on the shuttle were recovered after each flight and inspected. So after each flight, they started to get an understanding of how often these failures were occurring. So, but keep in mind, by the time the Space Shuttle Challenger flew on this particular mission, it was only the 26th flight of the shuttle ever. So the data set is fairly sparse, right? So there is not a large, statistically significant set of data, but it is enough that you can discern a pattern. So in the investigation report, there are a couple tables presented of data that was collected from the O-rings of each of these solid rocket boosters under each flight. And the way it was presented, apparently, to the management at the time when they were discussing whether or not to fly the shuttle, was that the engineers kind of felt that there was an issue with, these are the engineers, I believe, at Thiokol, thought there was an issue with temperature. As the temperature went down, they were likely to see more failures. And of course, the flight 51L, which was the Challenger flight that actually failed, was projected to be the coldest ever launch conditions for the shuttle at this time. And so there was some concern about whether or not we could fly the vehicle. But the data presented showed a very limited data set. It only showed the particular flights in which an actual measured problem incident, if you will, on the O-ring had occurred. And so if you look at the chart that was presented, there's not really a strong statistical correlation here. I mean, you only have 1, 2, 3, 4, 5, 6 data points, right? And that's barely enough to make any trend, and the data is not very consistent. So even the trend that you can make from this is pretty wild. In fact, at first glance, you might even think it is a flat line. You could draw some, parabolic shapes through here. It really doesn't tell you much. And so I think that that kind of communication fell flat, as in it's not clear to anybody that this tells you there's a problem. And so that has to do with how the data is presented, because this is not the whole story. Now, obviously, there were other engineers that were concerned that some of these failures that were reported really didn't have anything to do with the temperature. It may have been there was some inspections, some pressure leak testing that was done in the system, and some of those, were suspected as either not measuring correctly or causing some problems in the O-rings. And so it may not have been that temperature was causing these kind of outliers, right, where we had on one flight up to 3 O-rings causing some sort of problem. And so, in fact, in that particular case, that flight, the 3 failures, 2 of them occurred on the same O-ring, which, you have a redundant set of O-rings so that if 2 of them fail, now you have a leak path completely through. The idea being that if one fails, the other one's there as a backup. But in this particular case, there was damage on 2 of them. Now, it didn't completely fail the O-ring, but it showed damage. And so that's an indication that, hey, it's possible that 2 of these could occur at the same time. But if I were drawing a flat line and say, on average, at most, 2 O-rings will fail. There are 6 total joints in the system. The chances of those 2 being on the same O-ring aren't necessarily great if they're kind of random. And so if this were purely a random occurrence, then, the odds are certainly far less than you might be making it out to be. And so that was kind of what fed into the decision to decide to go ahead and fly the shuttle, amongst a variety of other factors, trying to get the flight going for political reasons, and a variety of other circumstances. But focusing in on the technical side of this and the data presentation, that what we're saying is this data set was presented very poorly. So the best example you can take on how to better present your data is shown in the next slide, which basically in the next table shows you, the data not just of the flights where there was an O-ring failure, but also includes the flights where there were no O-ring failures. And so what that starts to show you is that, as the temperature goes up, there are fewer and fewer, right? Of the number of launches that had failures, anything below 65 degrees had some problem, right? Anything above 65 degrees, there was an occasional problem, but it got, less. And when you look at the statistics, there's a very low probability as the temperature goes up that anything's going to have a problem. And so, it comes down to how you present the data. Now, I would argue you should be able to take this a step further, right? This is just showing data points. But if you can show a trend and explain how you're developing that trend, that's even more powerful. So in an example to represent this, I have taken that data from the launches up to this point and replotted them here in Excel. So on the left is all the data I've got that represents the particular flights, the temperatures at the launch conditions, the number of O-ring issues, they call distress technically, which doesn't necessarily mean failure. It may be just damage, and whether or not there was an incident. So the first diagram that we created represents what was presented at the time without exploring all of the flights, only the flights that had incidents. And of course, it looks kind of odd. You could come in here and put a trend line for this data series and say, well, it kind of looks fairly flat. And if I project it out back to, say, lower temperatures where we're expecting to launch, it's only saying that maybe 2 of the O-rings will fail, right? Which is about what we've seen on most flights up to this point. Now, it's still not good. There's probably a design issue that needs to get worked out, but engineers hadn't figured all that out yet. So, that you're looking at an argument of, well, the chances are we're going to see the same kind of failures we've flown on every flight up to this point. So what's the problem? So from a manager's standpoint, they're not understanding the issue that's being communicated by the engineers. And that is a problem, because if the engineers truly have an issue here that they understand, but they're not clearly communicating it, that's a failure on the engineers to do a good job of explaining the problem. Now, if you just flat out ignored the data, that's also a problem, because, as an engineer, you need to understand the full perspective, right? There's a lot more to it than just the cases that go wrong. So if we take the data that includes all the flights up to this point, including those that had no failures, well, you can run a trend line for this. And in this case, a straight line's not necessarily the best fit. You can also look at something like a polynomial projection for this, and reality might be somewhere different, but you project this out, and this is saying, well, if I launch at roughly 40 degrees Fahrenheit, and it was actually a little bit colder than that, I'm projecting 6 O-ring failures. Well, there are only 6 joints, so the probability that any one of those is going to fall on the same joint is pretty high. In fact, when you do the statistics on that, it's almost guaranteed. And so, you can see just by presenting the data differently and projecting it in a clear pattern, you can say, ooh, this is really a bad idea, and here's why we think this is a bad idea. Now, there's still probably some room for argument that this data is a little bit scattered, but statistically speaking, this is a much better representation of the data at the time. And it's basically telling you that you are certain to have a failure on the solid rocket booster, and that's obviously what occurred. So the data was really representative of what was really happening, but it wasn't communicated clearly. It wasn't presented in a way that makes it very easy for the managers to understand the problem at hand and make the right decision. So I say this mostly to remind you as an engineer, when you're presenting, whether you're putting presentations together for design reviews, whether you're writing reports, it's important to look at the data and make sure you are presenting it in the most clear possible way. Make sure you understand, look at the data you have in terms of which axes, what variables should I use, what other things have I forgotten about. Ask others to look at the data and the plots that you put together to make sure you're not missing something. Make sure your axes, are labeled appropriately. They're scaled appropriately. One of the things I see a lot with stress engineers is they will plot a couple different examples of, for example, a stress plot on a structure, and they use completely different scales. And, while the automatic scale is great to save you time, it doesn't always help you understand the issue at hand, especially if you're comparing a one versus another and you're using completely different scales. It doesn't make it very obvious, whereas if you set the scales the same, the stress concentration areas can be very clearly identified because they're using the same color scales. In other cases, I've seen folks using very different scales, and it makes it really hard to even understand what you're comparing here, right? So you need to spend some time understanding how you're presenting your data, who is the audience, what are you trying to communicate in terms of a story, and make sure that you've built your diagrams and the information in such a manner to tell that story. So that's just a short story on how you can learn from the disasters of the past, things that have affected us, and and there will be more in the future. As much as we try to prevent it, we are fallible humans, and we must just do everything we can to try and learn the lessons from accidents like Challenger and others, and improve our skills, improve the way we communicate, such that we're all learning from each other and making good decisions. So that's what I wanted to present on that topic. So I hope that was a useful, sidetrack for you. There's a lot more we can go into on the Challenger disaster, as well as others, lessons to be learned, and so we'll be doing more of that in the future. That's all for this episode of Engineering Aerospace. Join us again for the next one, and we'll see you then.